Hello everyone, welcome to this technology and process learning series. These videos have been created for all engineers across the company to help us build a stronger common understanding of the technologies we work with, the processes we follow, and the standards we must maintain as we develop advanced unmanned systems. As engineers, our work is not only about solving technical problems, it is also about building reliable, repeatable, and mission-ready systems. I encourage each of you to approach these sessions with curiosity to learn more, to know more, and to understand the boundaries of engineering that already exist in this world. I will now hand over to Rima to begin today's session.
Welcome to the Navigation Camera Training Program. In this session, you will build the practical knowledge needed to select, integrate, test, and troubleshoot camera systems for an unmanned ground vehicle. This program will strengthen your engineering judgment and help you design reliable vision systems that perform confidently across real-world missions and challenging environments.
Welcome to this camera engineering series. In this course, we'll build a strong foundation in understanding cameras used in robotics, unmanned ground vehicles, and autonomous systems. The series is divided into 5 parts. We'll begin with camera fundamentals, where we'll understand the core concepts every engineer should know. Next, we'll explore types of cameras, learning how different cameras work and how they capture images. Next, we have image formation, where we study topics like frame rates, exposure, shutters, etc. In the 4th part, we'll focus on image quality, covering the factors that determine how clear and reliable an image really is. Finally, we'll look at system integration, where we'll see how cameras are connected, configured, and deployed in real-world UGV applications. Let's get started. Before we start, let us understand how a camera really works. We will go through the building blocks of a navigation camera next. A navigation camera works by converting light from the environment into a digital video stream. First, the lens collects and focuses light, while the aperture and shutter control how much light reaches the sensor and for how long. The CMOS image sensor then converts this light into electrical signals. Next, the camera's image processor corrects color, exposure, noise, distortion, and low light performance. These processed images are captured as continuous frames based on the selected FPS and then compressed using formats such as H.264 or H.265. Finally, the video is transmitted through interfaces such as GMSL, Ethernet, MIPI, or USB to the onboard computer and ground control station, where it supports vehicle navigation and operator awareness. Now that we have seen how a basic camera works, let's dive into the training series. Welcome to Part 1, Camera Fundamentals. Before we dive into advanced camera technologies, it's important to understand the 5 building blocks that define every camera. We'll begin with resolution, which determines how much detail an image can capture. Next is field of view, which defines how much of the surrounding scene the camera can see. We'll then explore focal length and how it influences magnification and viewing angle. After that, we'll understand sensor size, which plays a major role in image quality and low light performance. Finally, we'll learn about pixel size and why 2 cameras with the same resolution can perform very differently. By the end of this section, you'll have a solid foundation for understanding for robotics and unmanned ground vehicle applications. In this image, we can see the same UGV navigation view shown at different resolutions, from VGA to 4K. In a navigation camera, resolution means the number of pixels captured in each image frame. A pixel is the smallest building block of a digital image, like a tiny square of color and brightness. When millions of pixels come together, they form the complete picture we see on the screen. More pixels usually mean more detail, but they also increase bandwidth, processing load, storage requirement, and sometimes latency. For an unmanned ground vehicle, resolution is not about maximum clarity alone. It is about choosing the right balance between detail, field of view, frame rate, latency, bandwidth, storage, and the actual mission requirement.
This image explains resolution using a simple LCD TV example. Resolution tells us how many pixels make up the image on the screen. The first number, 1920, represents the horizontal pixels across the width of the display. The second number, 1080, represents the vertical pixels from top to bottom. A pixel is the smallest unit of the image, like a tiny colored dot. When millions of pixels combine, they create the full picture. Higher resolution usually gives more detail and clarity, but it also increases data, storage, and processing requirements.
This image shows the difference between low resolution and high resolution. In the low resolution version, the image has fewer pixels, so details appear blurred, blocky, or less clear. In the high resolution version, the same image has many more pixels, so edges look sharper, objects are easier to identify, and the overall picture looks more realistic. For a UGV navigation camera, this difference is important because better resolution can help the operator see terrain, obstacles, and movement more clearly. This table helps us choose the right camera resolution based on where the camera is used on the UGV. For the front driving camera, 1080p or 2K gives a good balance of detail, latency, and bandwidth. Rear and side cameras can often use 720p or 1080p because their main role is reversing, coverage, and situational awareness. Thermal cameras may have lower resolution, such as 640 by 512, because contrast is often more important than megapixels. For surveillance or mission recording, 2K or 4K is useful for zoom, evidence, and post-mission review. For AI perception, the resolution depends on detection range and compute capability. The key point is simple. Choose resolution based on mission need, not just the highest number. Let's take a quick look at our agenda. We've now completed the first topic, resolution, and have built a solid understanding of how image detail is measured. Next, we'll move on to field of view, where we'll learn how much of the scene a camera can capture and why selecting the right viewing angle is critical for navigation, situational awareness, and perception in UGV applications. Let's get started. Field of view simply means how much area a camera can see. A wide field of view is like looking through a large window. You can see more of the road and surroundings, but objects may look smaller. A narrow field of view is like looking through a tube. You see less area, but distant objects appear larger and clearer. An ultra-wide or fisheye camera can see almost everything around it, but the image may look curved or distorted. For a UGV, wide cameras are useful for navigation and situational awareness, while narrow cameras are better for long-range observation. The right choice depends on the mission.
This image explains the three main types of camera field of view. Horizontal FOV shows how much of the scene the camera can see from left to right, which is important for road coverage and reducing blind spots. Vertical FOV shows how much is visible from top to bottom, helping the UGV detect the ground, slopes, and nearby obstacles. Diagonal FOV measures the view from one corner of the image to the opposite corner and is commonly used in camera datasheets. For unmanned ground vehicle integration, horizontal and vertical FOV are usually more useful because they directly relate to practical coverage and vehicle visibility. In this image, the soldier remains at the same distance, but appears very different because the field of view changes. With a wide FOV, more of the road and surroundings are visible, but the soldier looks smaller. With a narrow FOV, less of the scene is visible, but the soldier appears much larger and easier to observe. With a fisheye FOV, the camera captures the maximum surrounding area, but the soldier appears smaller and the image becomes curved and distorted. This shows the key trade-off. Wider views improve awareness, while narrower views provide better detail on the target. This image shows why resolution and field of view must always be considered together. Resolution tells us how many pixels are available, while field of view decides how widely those pixels are spread across the scene. With the same 1080p resolution, a wide 120-20-degree view captures more surroundings, but the soldier appears smaller and receives fewer pixels. A narrow 60-degree view shows less area but places more pixels on the soldier, making the target clearer. If the field of view remains the same, increasing resolution improves detail. For a UGV, the correct balance depends on whether the mission prioritizes wide situational awareness or long-range target visibility. For a UGV, the recommended field of view depends on the camera's role. The front navigation camera typically uses 90 to 120 degrees, giving the operator a clear view of the path and nearby obstacles. The rear camera is usually wider, around 100 to 140 degrees, to support safe reversing. Side cameras commonly use 90 to 120 degrees for flank awareness. Surround view cameras need an ultra-wide 150 to 180 degrees to minimize blind spots. Long-range observation cameras use a narrow field of view, allowing distant objects to appear larger and more detailed.
Let's return to our agenda. We've now completed field of view and understand how it determines the area a camera can observe. Next, we'll explore focal length, the parameter that controls magnification and directly influences the camera's viewing angle. By understanding focal length, you'll learn how to choose the right lens for different UGV and robotics applications. Let's begin. Focal length is the distance between the camera lens and the image sensor. It is usually measured in millimeters, such as 2.8 mm, 4 mm, 6 mm, or 12 mm. In practical terms, focal length decides two important things: how wide an area the camera can see, how large or small objects appear in the image. In simple terms, a short focal length is like looking through a wide window. You can see more of the road, terrain, and nearby obstacles, but distant objects appear smaller. A long focal length is like looking through a telescope. You see less of the surroundings, but distant objects appear larger and more detailed. For a navigation camera, focal length must be selected together with sensor size, resolution, mounting position, and mission range. The correct choice balances wide situational awareness with the detail needed on important objects.
Focal length alone does not completely determine a camera's field of view. Sensor size also plays an important role. The same 4mm lens will produce a wider view on a larger sensor and a narrower view on a smaller sensor. The formula shown here explains this relationship. Field of view is equal to 2 times the inverse tangent of the sensor dimension divided by twice the focal length. In simple terms, when the sensor dimension increases, the field of view becomes wider. When focal length increases, the field of view becomes narrower. For navigation cameras, engineers should always evaluate sensor size and focal length together to achieve the required road coverage, target detail, and mission visibility. This table provides a practical starting configuration for selecting camera lenses on an unmanned ground vehicle. The front primary navigation camera uses around 3.6 millimeters for a balanced view of the path ahead. A 6mm secondary front camera provides a narrower view with better target detail. Rear and side cameras use shorter focal lengths for wider coverage and fewer blind spots. Fisheye lenses support surround awareness, while mast and thermal observation cameras use longer focal lengths for distant viewing. These values are starting points only. Final selection must consider sensor size, required field of view, mounting height, target distance, and mission role.
Let's revisit our agenda. We've now completed focal length and seen how it affects magnification and the camera's field of view. Next, we'll explore sensor, one of the most important factors influencing image quality, low light performance, and overall camera capability. Understanding sensor size will help you make better camera selection decisions for robotics and UGV applications. Let's get started.
A camera sensor is the electronic component that captures the light focused by the lens and converts it into a digital image. It works much like the retina in the human eye. The sensor contains millions of light-sensitive pixels, and each pixel measures the brightness and color of a small part of the scene. These signals are then processed to create each video frame. In a navigation camera, sensor quality directly affects image clarity, low light performance, noise, and dynamic range, making it one of the most important components in the camera system. Sensor size means the physical dimensions of the light-sensitive area inside the camera. In simple terms, a larger sensor is like a bigger bucket collecting rain. It can usually collect more light. This often gives cleaner images, better low-light performance, and less noise. A smaller sensor can still provide good resolution, but its pixels may collect less light. Sensor size also affects field of view. With the same lens, a larger sensor gives a wider view, while a smaller sensor gives a narrower view. That is why engineers must evaluate sensor size together with focal length, resolution, and mission needs. A CMOS sensor is an electronic image sensor used inside most modern digital cameras, including navigation cameras for UGVs. CMOS stands for Complementary Metal Oxide Semiconductor. Its job is to convert the light focused by the camera lens into electrical signals, which are then processed into a digital image or video frame. This image shows the basic internal structure of a CMOS sensor. Light first passes through the protective cover glass, which shields the sensor surface. Microlenses then focus the incoming light onto individual pixels. A color filter array separates the light into red, green, and blue information. Below this, the pixel array converts the light into electrical charge. The readout circuitry transfers these signals, while the amplifier and analog-to-digital converter turn them into digital data. Internal metal layers carry power and signals through the sensor, and the silicon substrate provides the main semiconductor structure. Finally, the output pins send the image data to the camera processor, where it becomes the digital image we see. This table compares common camera sensor sizes from very small 1 by 4 inch sensors to much larger APS-C and full-frame formats. As sensor size increases, light collection and image quality can improve, but camera size, cost, and integration complexity also increase. For UGV navigation cameras, 1 by 2.8 inch and 1 by 2.3 inch sensors are common practical options because they provide a useful balance of image quality, size, cost, and ruggedness. One important point is that names such as 1 by 2.8 inch do not directly equal the actual physical width of the sensor. They are legacy industry format names, so engineers should always check the actual sensor dimensions in the datasheet. This table compares selected Sony and onsemi image sensors that may be considered for automotive and UGV camera applications. It shows that sensor size, resolution, and pixel size vary significantly across models. For example, sensors such as the IMX3T90 and AR0233AT use larger 3 micrometer pixels, which can support good low-light performance. Higher resolution sensors such as the IMX728, AR0820AT, and R2020 use smaller pixels to capture more detail. The key point is that a larger optical format can collect more light, but overall image quality also depends on pixel size, sensor design, and image processing.
Let us understand the navigation camera ecosystems and its players. The camera ecosystem can be understood in 3 layers. Layer 1 includes image sensor manufacturers such as Sony and Onsemi. These companies create the CMOS imaging chip, the core component that captures light and converts it into digital image data. Layer 2 includes camera module manufacturers such as Econ Systems and Leopard Imaging. They use sensors from Layer 1 and add the lens, electronics, ISP, interface, connectors, and housing to create a complete camera module. Layer 3 includes system integrators and automotive Tier 1 companies such as Bosch and Valeo. They take the camera hardware and add software, calibration, diagnostics, safety functions, and vehicle integration. So in simple terms, Layer 1 makes the sensor, Layer 2 builds the camera, and Layer 3 delivers the complete vehicle-ready vision system. This slide compares representative automotive image sensors from Sony and Onsemi, two of the leading companies in CMOS imaging technology. Sony models such as the IMX390, IMX490, and IMX728 cover applications ranging from surround view and UGV navigation to high-resolution autonomous driving. Similarly, Onsemi sensors such as the AR0233AT, AR0820AT, AR2020AT support navigation, front-facing ADAS, and long-range perception. The table compares each sensor by resolution, typical horizontal field of view, and common vehicle application. One important point to remember is that Sony and Onsemi manufacture the image sensor itself. The final field of view depends mainly on the lens and camera module selected by the integrator. This comparison helps us understand how different sensors are matched to different vehicle vision requirements.
This slide compares representative GMSL2 automotive navigation cameras from Econ Systems and Leopard Imaging. Both companies operate at the camera module level. They take image sensors from companies such as Sony, Onsemi, and Omnivision and integrate them with lenses, electronics, interfaces, and housings. The Econ Systems examples include the Nilcam 81, Sturdicam 88, and Sturdicam 31, covering applications such as HDR navigation, front vision, surround perception, and NVIDIA Jetson integration. Leopard Imaging offers modules such as the IMX728, OX08D10, and OX03F10 based cameras, with field of view options ranging from narrow angle long range perception to ultra wide surround vision. The key takeaway is that resolution comes from the sensor, while the final field of view depends mainly on the lens and camera module configuration. This slide compares representative automotive navigation camera systems from Bosch and Valeo, two major Tier 1 suppliers to the global vehicle industry. Bosch offers front-facing systems such as the MPC3 and MPC2, which support applications including lane detection, traffic sign recognition, object detection, and driver assistance. Its surround view cameras provide much wider coverage for parking and low-speed navigation. Valeo follows a similar structure, with front vision cameras for forward ADAS and surround view systems for close-range awareness. Its Panavision camera platform supports wider fields of view for autonomous driving and surround perception. The key point is that Bosch and Valeo deliver complete vehicle-ready systems, not just camera modules. Their solutions typically include sensors, optics, processing, calibration, diagnostics, software, and vehicle-specific integration.
Let's take one last look at our agenda. We've now completed sensor size and understand how it influences image quality and low-light performance. Next, we'll explore pixel size, the size of each individual pixel on the image sensor. You'll see why two cameras with the same resolution can produce very different results, especially in challenging lighting conditions. Let's begin. Pixel size is the physical size of each light-sensitive pixel on a camera sensor. It is usually measured in micrometers, written as me. For example, 1.4 micrometers pixel, or 2.1 micrometers pixel, or 3.0 micrometers pixel. In simple terms, each pixel works like a tiny bucket collecting light. A larger pixel collects more light, which usually gives a stronger signal, lower noise, and better performance at night or in shadows. A smaller pixel collects less light, but allows more pixels to fit on the same sensor, increasing resolution and detail in good lighting. For a navigation camera, pixel size must be balanced with sensor size, resolution, low light performance, and mission needs.
This image compares two cameras using the same general sensor area. Camera A has fewer but larger 3 micrometer pixels, so each pixel can collect more light. This produces a brighter, cleaner image in low light conditions. Camera B has many more, smaller 2.1 micrometer pixels. Because each pixel has less surface area, it collects less light during the same exposure, so the image appears darker and may need more gain. Camera B can capture more detail in good lighting, but camera A is often better for night navigation. The key trade-off is low light sensitivity versus higher resolution. This table brings together the key starting parameters for a UGV camera system. Front navigation cameras need a balanced combination of 1080p class resolution, wide field of view, short focal length, and larger pixels for dependable low-light driving. Secondary front cameras can use higher resolution and a narrower view for better target detail. Rear and side cameras prioritize wider coverage and reduce blind spots. Thermal navigation cameras support safe movement in darkness, while thermal observation cameras use narrower fields of view and longer focal lengths for distant detection. These values are starting points only. Final selection must be validated against sensor size, mounting position, target distance, bandwidth, latency, and mission requirements. This brings us to the end of Part 1, Camera Specifications. We have covered the key fundamentals, including resolution, field of view, focal length, sensor size, and pixel size. I hope you found this first video useful and relevant to your engineering work. In the next part, we will move on to types of cameras and understand where each type fits in an unmanned ground vehicle. Stay curious, take notes, and keep connecting these concepts to real vehicle requirements.